Good evening, everybody. Welcome to the June 16th version of the Virtual Night Sky. Glad to see everybody today. I wanted to just kind of give you an introduction about how the show is going to run tonight. Welcome, everybody. We know we always have some new visitors, and so if this is your first time joining us, you'll sort of see how this works, and hopefully you'll come back and join us a number of other times. And we also know that people have been following us for quite some time, so welcome back. Tonight, the main focus is going to be about the summer solstice, and it's coming up next Sunday is the longest day of the year. We're going to talk about that a little bit at the end and some of the cultural significance of the summer solstice. But in the first part of our program, we have a very important guest speaker that's going to talk to us about all things sun. After that, there will be a question and answer period, and then we will invite some of the team from LROC, Lunar Reconnaissance Orbiter Camera, and because we've been celebrating the moon this month in June, and they have a little presentation about eclipses, and we're celebrating an anniversary for LROC in a couple of days, so they'll tell us about that. I will then be on for a little bit to talk a little bit about the solstice, and then we have some updates and some astronomy in the news, and that's how we're going to complete our program today. We'll give you some insight into what's coming up in future programs as well. So I am going to very quickly just kind of go over some housekeeping. This is a webinar format, so we don't allow people to chat. That's just been disabled, but we do encourage you to ask questions. And so you have a question and answer button on your keyboard. Please go ahead and just activate it, send out a question. What happens on our end is that there are some students in the background, I'll introduce them in a minute, that are working those questions, and they'll answer them, and they're going to pick out key questions to turn over to your presenters during the question and answer breaks as well. There are some poll questions for the audience, so watch for that as we go along tonight. We do closed caption our program, and so if for some reason you don't want to see that, there is a closed caption button. You can actually set it up so you could either have it on or off if you want. It makes it easier for us to capture the recordings at the end of the show. So those are the things that we have to talk about. Introducing tonight, our webmaster is Kim Baptista. She's the one that handles all the communication, gets this set up, keeps us organized, and keeps us on our toes. So thank you, Kim, for all of your support for this last little bit more than a year. We also have Meg Hufford, a colleague of mine. She and I are the ones that conspire to do outreach programs at the building that is behind me. That is ISTB4 on the Tempe main campus. We've been closed for COVID. We're not doing public programs right now. We expect to get back to them at some point, but until then, we're going to just meet virtually, and we're going to try this every other week for the foreseeable future, just to keep everybody on their toes. We have 3 students that have been with us for the entire program here for over a year. So Alex Blanche is with us, Alicia Hyatt, and Spurti Kachere. You're going to hear more about Spurti today because we're kind of celebrating a milestone with her today too. So without any further ado, that's all the housekeeping. That's how things are going to work. I'd love to introduce Katrina Bossert. She is a new professor for us at the School of Earth and Space Exploration. She's been with us just a little bit less than a year now, and she's a physicist, and she studies near space, and I'm talking about near space, just basically in the environment around the Earth. And one of the reasons I called on her to come tonight is because she does have a really good academic understanding of the sun and the influence of the sun on the Earth. And so this is going to be a really good astronomical look at the sun. We're turning ourselves away from the outside stars in the nighttime sky, and because of the solstice coming up, we're celebrating the sun. So I'm going to ask Katrina to join us and introduce yourself. Thank you very much.
Hi, would you like me to share my screen? And
yes, please.
Start the presentation.
And you're off and going. Is this your first summer here in Phoenix?
Yeah.
It is. Okay. Well, welcome to Phoenix.
Speaking of the sun.
Like. Yes, speaking of the sun, this is what it's like.
All right, the sun. And let me go ahead. All right, so the sun is a star at the center of our solar system. It's one of 10 to the 11th stars in our galaxy. So we're talking one of billions of stars in the galaxy. It has an average radius of about 696,000 kilometers, or about 109 times the radius of Earth. And in this picture here, we have the Earth shown for comparison against a subset of the sun, and it would take over 1 million Earths to fill the volume of the sun. The sun makes up 99.8% of the mass in our solar system. Just how much energy does the sun produce? Well, I have a big number for you, about 3.85 times 10 to the 26 watts. And this is the equivalent of about 9.92 times 10 to the 16th tons of TNT exploding in 1 second. So that's a pretty large number. Let's put that in perspective. If we were to put TNT spread out over the entire Earth at a 1 meter thickness, and we exploded it, it would still result in less than 1/100th of the energy emitted by the sun in 1 single second. Only a fraction of that energy produced by the sun reaches our Earth, though. And the solar constant gives us a value of the flux density measured at the surface of the Earth. That's about 1370 watts per meter squared, or 1,370, or to be exact, 67 watts per meter squared. The sun's energy that reaches the Earth is about 35,000 times the amount of energy currently used by people on Earth. So it's estimated that just covering a section of Earth about the size of New Mexico with solar panels could provide enough electricity for the entire globe. So the sun itself consists of just spherical layers of gravitationally stratified gas. We know the composition of the sun based on the absorption and emission lines. And we know that the bulk of the sun's mass lies in its core, which is also where the fusion of hydrogen to make helium occurs. The sun's core is very, very hot. It's about 15 million degrees Kelvin. So let's talk a little bit more about this structure of the sun. We have that core at the center. It's about 0.25% of the sun's radius. Outside of that, we have the radiative zone. So that's where we start to get that energy radiating into the sun. And then above that, we have the convective zone, which is where we have all of this heat from the radiative zone rise up, and then it cools at the surface and falls back down. An interesting fact is that it takes photons generated at the core of the sun about 170,000 years to reach the surface of the sun. The effective surface of the sun is actually the photosphere. So this is what we see. This is where most of the photons that we are seeing on Earth come from. And that is a lot cooler than the core, ranging from about 4,500 to 6,000 degrees Kelvin. Above the photosphere, we have the chromosphere, and that's where we start to see these spicules and things spiking out. That temperature rises up to about 8,000 degrees Kelvin, but the density is very rapidly dropping off, so we don't see as many emissions from the chromosphere. And then the corona, which if you've ever watched a solar eclipse, you can see that sun's corona going off, and it actually expands millions and millions of miles into space. It's also very, very hot and can reach a couple million degrees Kelvin. So sunspots are a common occurrence on the sun, and they're often about 1,500 degrees Kelvin cooler than the surrounding regions of the photosphere. And they're occurring on that photosphere surface. So because they're cooler, they appear darker, and they're caused by these kinks in the magnetic field, and they inhibit convection on the sun. And what actually happens is you often see sunspots occurring in groups or pairs, and you can see magnetic field lines originating from these sunspot regions. So they're opposing polarity. Another thing about sunspots is that they are linked with solar maximum. So I have an image over here showing the sun at solar maximum, and you can see all these regions of sunspots. And then during solar minimum, or closer to solar minimum, it's not uncommon to see a sun with absolutely no sunspots on it. And measurements of the sunspots were really how we did our earliest studies of the sun. So as soon as this advent of the telescope was used to study the sun, we started recording these sunspots. And what was found was that we had these times of high sunspot counts and low sunspot counts. And after we took data for many, many decades, it looked like there was a cycle that was on average about 11 years. This 11-year period where we see this sunspots increase and then decrease, this is actually known as the solar cycle. Another interesting aspect of the sun, or some phenomenon that occurs with the sun, is something called a coronal mass ejection, or also referred to as a CME. It can contain over 1 trillion kilograms of material. That's equivalent in mass to over 250,000 aircraft carriers. And this mass is sent hurling into space at speeds of over 1,000 kilometers per second. A typical CME has an associated energy of 5 × 10⁻⁴ joules. And that is the equivalent energy of about 50 million hydrogen bombs. Solar flares are another aspect that occurs on the sun. These are a sudden flash of increased brightness, and they can last from minutes to hours. They result in powerful bursts of X-rays that reach the Earth. And these X-rays and this radiation can actually alter the upper atmosphere of Earth, which disrupts long-range radio communications. And the radiation released by solar flares can also be harmful to satellites as well. We like to view the sun at different wavelengths in order to study different processes in different regions. The hottest regions, like the sun's corona and solar flares, are going to emit a lot more radiation in the X-ray region. So we can use shorter wavelengths to study these regions. And sunspots have enough of a difference in the visible, that we can see a difference in visible light from a sunspot in the surrounding photosphere just because of that significant decrease in temperature. So courtesy of NASA, there are all these different comparisons of different ways to image the sun here, which I think is pretty nice to look at. So some more fun pictures of the sun. I'm going to give just a few images here. This image is actually what we call granulation. So on the surface of the sun, we get all these regions of plasma bubbling up, and it's very hot, and then it bubbles up and then it sinks again. So this is this convection, and where it's sinking is where we see the darker black lines of that cooling plasma sinking back into the sun. So that's a nice image with a resolution of about 30 kilometers. Here's another example. All these little spots here are also that same granulation effect, and they are surrounding a sunspot. So you can see these sunspots are quite large. And here's what we call coronal loops, these really smooth magnetic field lines that rise up from the sun and connect back to the sun again. And they're very, very hot lines of plasma that extend into the sun's corona. Coronal holes are these regions of the corona where we just have magnetic field lines extending way out from the sun. And what happens is, because of these extended magnetic field lines, we start to get a flow of lots of material away from the sun. So we often see increased solar winds associated with these coronal holes. This is a combined image of high energy X-rays and extreme ultraviolet radiation with multiple instruments. And I like this image because this red and this yellow, this is extreme ultraviolet. This is what the corona, we're seeing corona here. But the absolute hottest regions are going to be the flare regions. And these are going to be the regions where we see the ultra short X-rays being emitted from the sun. So we mentioned the solar cycle, and this increase in sunspots every 11 years. And what's actually happening is every 11 years, the sun's magnetic field flips. So near the time of the magnetic field flip, the sun's magnetic field becomes more complex. The sun becomes more active. These are some plots down here comparing the sun's magnetic field. This is closer to solar maximum, and the field lines become more complex. The top image is closer to solar minimum, and the sun's magnetic field is less active. So solar maximum is that time where we're seeing the flip in the magnetic field polarity. And again, you see this increase in sunspots, you see increases in solar flares, coronal mass ejections, all of these things occurring during solar maximum. I like this image too. We've got a comparison of what the sun looks like during solar maximum versus during solar minimum. And the next projected solar maximum is in 2025. So we're coming out of the solar minimum and we're starting to see some increase in solar activity. Actually, this past year, we've actually even had a few geomagnetic storms, nothing extreme, but definitely significant enough to say, hey, the sun's starting to wake up. So the solar wind is this other thing that's very important when we talk about space weather and the interaction of the sun with the planets. Typical velocity ranges from about 250 to 750 kilometers per second. Usually we have average values around 400 kilometers per second. The solar wind can be faster and denser, especially during active solar times. And it's made up mainly of protons and electrons, and we get a few other trace elements in there as well. The solar wind itself is filled with these very, very fast moving particles. And so while it's not very dense, we have high energy particles. The other aspect of the solar wind is that these particles have an associated magnetic field. So we have these particles that are spewing from the sun. They have a charge, they have an energy associated with them, and they have a magnetic field associated with them. And they come and they interact with Earth's magnetic field. And it's the collision of these high energy charged particles and their associated magnetic field with Earth's magnetic field that results in this impact that we see on Earth. Now, the heliosphere, while we're talking about this extending solar wind and extending magnetic field from the sun, this heliosphere is really the region of sun's influence. It's the solar wind expanding into space. It's previously been defined as where the speeds of the solar wind are supersonic or faster than the speed of sound. So we've got something that's extending millions of miles into space. And it's said that the closest boundary is thought to be about 100 times the distance from the Earth to the sun. And we learned more about the heliosphere and the edge of the heliosphere with the Voyager 1 and the Voyager 2 missions. We know that the heliosphere forms a protective barrier around the sun and the solar system through the solar wind and the associated magnetic field. Outside of the heliosphere in the interstellar region, the particles from our sun rapidly decrease, and then we see an increase, a sharp increase in these high energy galactic cosmic rays. And galactic cosmic rays from outside of our solar system are very, very high energy. If it weren't for the sun, they would constantly be pelting our Earth. And their energy is high enough to penetrate the Earth, or at least penetrate the atmosphere and generate other high energy particles. So they can be pretty dangerous. Now, let's come back to Earth and let's talk about the Aurora, which is interesting not only for Earth, but also for some of the other planets in our solar system. So what happens is we have on the day side of Earth, we've got this exposure to the solar wind, and the solar winds then on the backside are kind of pulling the magnetic field away, and we get what's called a magnetotail. And all of this energy builds up in the Earth's magnetic field. And then what happens is this snaps like a rubber band. It almost pops back, and it causes this burst of high energy particles back towards the Earth, guided along the Earth's magnetic field lines. And so we see this particle precipitation at the poles. And this is what results in this beautiful display of the aurora on the night side of the Earth. Now, there are numerous emission lines that arise from this aurora and particle precipitation, hundreds, in fact, but the most commonly observed colors, the ones that everybody sees, are typically red and green. They're the strongest and they're the ones that we can see. We get a lot of emissions in the UV and the infrared, but we can't see those. So I'll just briefly talk about this red and green aurora. The red aurora occurs at higher altitudes from about 250 to 350 kilometers. This is generated by excited atomic oxygen. And this particular energy state of oxygen is quickly quenched, which means it bumps into another atom at lower altitudes, and so it doesn't emit. Another thing about this is that the photon emitted between states cannot happen until, you know, this relaxation time is about 110 seconds. So this excited atom is moving around for a while before it emits. So this aurora typically looks quite diffuse. And the green aurora is very bright. It occurs between 95 and 100 kilometers. It's actually generated by atomic oxygen as well, but a different excited state. And this typically gets quenched below 95 kilometers. So now, what causes these colorful aurora and the severe geomagnetic storms that cause the very spectacular aurora? Well, as we mentioned, we get disturbances from Earth's magnetic field. And the solar wind plays a huge role in producing these geomagnetic storms. So the larger geomagnetic storms are often associated with coronal mass ejections. So when we get this burst of material from the sun with a really strong velocity, that's going to be what causes the largest geomagnetic storms. It oftentimes takes the solar wind on average several days to reach the Earth, but a stronger storm, a stronger coronal mass ejection can reach the Earth in as little as 18 hours. And geomagnetic storms can last a few hours, but the really strong ones can even last a few days. So the strongest known geomagnetic storm took place in 1859. This was called the Carrington event. And this storm wreaked havoc on telegraph systems at the time. Of course, now we are far more technologically dependent, and having a Carrington event hit now would be concerning. This particular event caused auroras that were seen as far south as Havana and Florida. I mean, brilliant displays. It's estimated that a similar event today would cost between 0.6 and 2.6 trillion in damages in the United States alone. So it's really important to be paying attention to space weather events. A weaker but strong event happened in 1989, and here's an example. The storm hit and caused all sorts of damage to ground-based systems in Quebec, and just destroyed transformers, left Quebec without power for the night. So this is just one example. And another thing to keep in mind as well, some of these places up north have done more preparation for solar storms. A strong, powerful geomagnetic storm would cause a lot of damage, especially to the lower 48, where most places are not prepared for something like this. Another thing to keep in mind as far as solar activity are radio blackouts. And this is going to be more, instead of the CME, this is going to be something that's caused more by the solar flare, by the X-rays and UV radiation. And this is something that affects high frequency communication. And what happens is when we get that really intense radiation, it ionizes Earth's atmosphere. And so it starts to absorb radio signals. This is an example of just a plot of regions that are affected by radio blackouts, something that's generated by this NOAA Space Weather Prediction Center. This is something that you often see on the day side because you're seeing that direct radiation from the sun, and that's what's causing this ionization. So an example of a recent radio blackout having some pretty significant effects here on Earth was back in 2017, just a series of unfortunate events. We had 3 hurricanes going through the Caribbean, and a solar flare on the morning of September 6th, 2017 caused radio communications to go down for most of the morning. It actually caused 90 minutes of communication loss with the cargo plane, and high frequency radio was unavailable for nearly 8 hours. This was a really big issue because this is a situation where people were extremely dependent on radio communications, especially with power being out in many of these places, and you know, trying to work on with emergency workers, and these hurricanes are just sweeping through. What makes it even worse is that right after this flare, a few days later, a second flare on September 10th also disrupted radio communications over the Caribbean. These are just some plots of the sun during these flares. This is the September 6th, and this was the September 10th. So, you know, these events, these solar flares can have certainly have some pretty significant influences, especially when they happen at the wrong time. Another thing that a lot of people don't consider is the influence of solar storms on satellite orbits. So satellites are actually still orbiting in atmosphere, and they do, especially in low orbit, experience drag because they're orbiting in the thermosphere. So an extreme storm can actually change the atmosphere in this region of low Earth orbit enough to pull a satellite farther off orbit in one day than that satellite would experience in a year. So solar storms can have very, very significant influences on satellites. Another problem here is that we're looking at thousands and thousands of pieces of large space debris now and trying to track these pieces of space debris. And so trying to understand how solar storms and space weather can impact the near space environment and change the environment for just orbiting debris is also a huge issue. You know, space debris can and does frequently collide with operational satellites and other debris. So we really want to pay attention to this and try and track these things and understand the space weather that can change these orbits. So, you know, not only are we becoming more technologically dependent society, we're also becoming a society that depends on space for things such as communication satellites. And so space weather is not only going to harm these satellites through energetic particles and radiation, but it can also disrupt orbit. So I want to talk about one final thing, and that is I want to talk about the sun's radiation and impacts on us, impacts on Earth's surface. And as we start to get more and more excited about space travel and visiting the moon again and visiting Mars, how does the sun's radiation and space radiation impact us? So let's give some baseline here. The average annual radiation dose per person in the US is about 6.2 millisieverts. And there are a lot of sources of radiation in our daily lives, and a lot of that radiation comes from naturally occurring sources on Earth. In fact, on the surface of the Earth, only about 5% of the radiation we experience comes from space. So now let's talk about what the human body can tolerate. The annual exposure limit for radiation workers in the US is 50 millisieverts. 100 millisieverts is the lowest annual dose in which there's any increase in cancer evident. A single 1 sievert dose is linked to an increase in cancer of about 5 out of 100 persons, and 5 out of 100 persons will develop fatal cancer. And a single dose of 10 sieverts will result in death. So now let's move up. We know that we don't get a lot of radiation exposure on the surface of the Earth, but what about flying? Well, one transatlantic flight results in about 0.1 millisievert of radiation exposure. Okay, so not lots. This is pretty minimal. Now, if you fly during a geomagnetic storm at higher latitudes, you could be exposed to 3 millisieverts per hour at cruising altitudes. And for an extreme solar storm, so an extreme event, you could actually be exposed up to 20 millisieverts for your flight. So you can start to be exposed to more significant radiation. Now, what about things like the International Space Station or staying on Mars? Well, average exposure on the International Space Station during quiet conditions is around 0.65 millisieverts per day. And of course, during storm time conditions, this can be raised to several millisieverts. But the International Space Station is still largely protected by the Earth's magnetic field. Now on Mars, it's actually quite similar, about 0.64 millisieverts per day. And that's because Mars actually has a thin atmosphere, which offers some protection from cosmic rays. Where the problem lies is this exposure in transit. So if we were to consider the radiation exposure in transit to Mars, you could actually, astronauts would be exposed to about 1.84 millisieverts per day, just due to galactic cosmic rays. A solar proton event could increase exposure from anywhere from 1 to almost 20 millisieverts. And it's estimated that during an 860-day mission to Mars, that includes the space transit time and time on Mars, an astronaut would be exposed to about 1 sievert. So our sun is in constant action, and it provides us with all the energy we need for life on Earth, but it can also cause these powerful storms. It pelts the Earth with radiation and high energy particles. And who knows when the next big solar storm could be. It could have some devastating impacts. And even moderate storms can be harmful to satellites and infrastructure. So the next solar maximum will be in 2025. And I mean, what will the next active period of the sun have in store for us? So with that, I would be happy to take questions. I think they have a poll here. So yeah.
Thank you very, very much. That's just exactly what we needed, a dose of the sun on in celebration of our solstice. So thank you. I think that's great. I have just one really quick question for you, and then I'm going to ask, I think Spurti will take some audience questions. But the last solar maximum did not, if I remember right, did not really turn out to be much of a solar maximum, right? I mean, it was kind of a benign maximum, big expectations, and then it was kind of soft. Is that right? Do I have that? Did I remember that?
Yeah, that's correct. It was pretty. It was a pretty mild solar maximum.
And so in the continuum of things, right, solar maximums over years, that was kind of a weak one. But we expect the one approaching, the one in 2025, to be back up to normal. And
we don't know. We don't know.
So that's why we have to keep track of our solar weather, I guess. All right. And then in just because all of that exposure and all that kind of stuff you're talking about, there really is nothing you can do flying, right? There's no place to sit on the plane or different thing to do. We just sort of accept that we're exposed in various ways during our regular journeys here or there, right? Is that how that works?
Yeah, I mean, they have discussed whether they should reroute planes during severe geomagnetic storms. But I mean, you're looking at a radiation exposure that's probably similar to a CAT scan.
So not horrible. All right, Spurti, did you have some audience questions?
Well, I'm here for the polls, and Alicia will be taking some questions.
Okay.
And before the polls, I'd just like to remind everybody that if you have any questions for Dr. Bosa, please enter them in the Q&A, and we make sure to get back to you. And I will be launching the poll right now. Okay, so what is the color of the peak emission wavelength of the sun? Green, yellow, orange, or red? Go ahead and cast your votes as Alicia takes some questions for Dr. Bosa. Alicia?
Thank you so much, Sue, and thank you, Dr. Bossert, for that wonderful presentation. We have a couple great questions for you, and the first kind of has to do with our poll question. So Jill is asking, is there a process of deciding the color of the images, or are they a reflection of the individual type of process that is used?
Oh, that's a good question. I don't have the answer. I don't know why they decide to color the images a certain way. Maybe a scientist thought it looked cool, or maybe there's something more to it, but I don't have the answer to that one.
That's all right. Thank you. Our next question, we actually have had multiple people ask, and we're going to take Kathy because I think she was first to ask. Why does the sun's magnetic field flip?
Oh boy. That's a really good question. It's something that's still being studied. And you know, I am not a heliophysicist. I don't study that aspect of the sun. I wish I had a better answer for you. But I could say that it's not something that is fully solved just yet.
But it is a regular occurrence, right? I mean, it really, that flip is something we can kind of count on to happen every 11 years, is it right?
Yeah. I mean, it has to do with the plasma rotation within the sun. And the sun itself is actually moving and rotating. And we actually do know that the plasma on the outside of the sun is rotating, and it has a rotation period of about 27 days. So actually, we do know if there's like a region of the sun that's particularly active or a really strong coronal hole, we can predict that, hey, we saw this go around once. It's possible that 27 days from now, we might have more solar activity facing Earth.
Excellent.
Wow. Thank you so much. And thank you for your presentation as well. I think we're going to turn it to Sue to give the results of our poll question.
Yes. Thank you, Alicia. So let's share the results. Oh, most people think it's red. Unfortunately, we tricked you yet again. It is not red. It is green. Is that right, Dr. Barsa?
Yep, the peak wavelength is closer to green based on the sun's temperature.
Excellent.
But our eyes are more adjusted to the
red,
yellowy and colors.
Perfect. Okay, thank you. So that's it from the polls and the questions, and back to you, Rick.
Thank you very much. So I mentioned it before at the beginning of the program, but June at the School of Earth and Space Exploration at ASU, it just happens to be Moon Month. There's a lot of lunar activity that happens. There's a lot of anniversaries. As you know, we have been celebrating the 50th anniversary of all of the Apollo landings and trying to keep track of when those happened 50 years ago. And so we've done a lot of lunar activity and programming to date. So in June, at each of our 3 virtual night skies, we've asked the people at Lunar Reconnaissance Orbiter Camera to kind of just come and give us a little session. And so tonight we have Jane Rector, and she will be talking a little bit about eclipses and also talking about a major anniversary for LROC that's coming up in a couple of days. Thank you, Jane.
Thank you. All right, let me get my presentation up.
And Jane, you're broadcasting from Northern California, if I hear this right. So, right?
I am.
We can work and we can be out of town and we can be on vacation at the same time. So thank you very much for sharing.
All righty. So thank you, Rick. Like he said, my name is Jane, and I'm here with the LROC science team to share a presentation with you guys about eclipses, their effects on LRO, and plus celebrate 2 very, very special anniversaries. The Lunar Reconnaissance Orbiter, also called LRO, was put into orbit in 2009 and is powered by solar arrays. It has 7 different science packages, one of which is the Lunar Reconnaissance Orbiter Camera, or LROC. The LROC consists of 3 cameras, 2 narrow-angle cameras and 1 wide-angle camera, mounted on the orbiter, which capture high-resolution images of the lunar surface. The image on the right shows the WAC, or the wide angle camera, the NAC, or the narrow angle camera, as well as the SCS, or the sequence and compressor system, which transfers commands from the spacecraft to the camera to get image data and receives and compresses the collected data prior to transmission. During solar eclipses, the moon passes in front of the sun and casts a shadow on the Earth. The moon continues to be lit by the sun, and the shadow is not big enough to completely darken the Earth. The photo here below, taken by Aaron Boyd, who is here answering questions today, was a total solar eclipse in Wyoming during 2017. During a lunar eclipse, the Earth passes in front of the sun and casts a shadow on the moon, completely covering it. I've included the dates for the next 2 solar and lunar eclipses in the bottom and a link for the known eclipses. So here in this photo is a close-up of a partial solar eclipse as the moon moves in front of the sun, and it's been seen from the surface of Earth. When the moon is backlit like this, you can see the mountains and the ridges around its surface, as well as the contrasting brightness of the sun and a collection of sunspots. LROC can also photograph solar eclipses from space instead of from the Earth. And to do so, the orbiter is turned 180 degrees to face Earth and uses the narrow angle cameras to take images. Solar eclipses appear as darkened patches on the Earth's surface, as seen in this photo to the left. And the X in the bottom right corner of the photo is the center of the shadow at the highest point of the eclipse, close to St. Louis and Nashville, where the eclipse would have been seen the best. In this video created by Ernie Wright, LRO's orbit is shown through a lunar eclipse where it passes behind the moon and comes out on the other side as the sun's light is being completely obscured. The meters at the bottom left of the video indicate how much sun LRO is getting throughout its orbit and show its battery level fluctuations during a total lunar eclipse. Lunar eclipses, unlike solar eclipses, are perilous for LRO and other solar-powered instruments that orbit the moon. As LRO orbits the moon, which is about once every 2 hours, it is without light for about 45 minutes. During a lunar eclipse, however, it can be without light for up to 4 hours as the light from the sun is obscured on the typically lit side of the moon. LRO's team can adjust its orbit to avoid as much of the eclipse's shadow as possible and take the safest path. To survive a lunar eclipse, all of LRO's instruments are turned off to conserve battery power, and survival heaters are turned on 24 hours beforehand to preheat LRO and prevent the orbiter from getting too cold during the prolonged night it experiences during an eclipse. During some lunar eclipses, like partial events where the risk to the orbiter is not as high as a total eclipse, LRO keeps some of its instruments on to collect data. LROC's WAC and Diviner instruments, a radiometer that can identify cold traps, have both been left on, which is how we took the picture to the right in 2010 and discovered the coldest measured temperatures on the lunar surface with Diviner. Now, June 18th marks LRO's 12th anniversary of launch. On the left, you can see the rocket that took LRO through our atmosphere. LROC's first picture, or what we call first light here, was taken 12 days later on the 30th of June. The picture to the right is one of the very first full-resolution NAC images ever taken and shows new and old craters on the lunar surface. LRO was only supposed to be a 1 to 2 year mission, and 10 years passed, it's still going. LRO's instruments have provided the largest volume of data ever collected during a planetary science mission and is unmatched in its contributions to science and exploration. LRO continues to aid in cutting-edge research of our moon and its implications for planetary science as a whole. And that's the end of my presentation, folks. Thank you guys for listening and celebrating LRO's anniversary with me, and I'll hand it back over to Rick for questions.
Thank you, Jane. Thank you. That's amazing. Absolutely amazing. So when we were doing this, we had a little rehearsal, just tell the audience, we had a little rehearsal yesterday, just to kind of get our act together and figure out who's going to do what. And when I saw those images of the moon shadow from a moon orbiter, I never really thought you know, it just never occurred to me that we would be orbiting around the moon and taking images of the moon as it passes through shadow. And it was really amazing. And then what were you telling us yesterday? There was something you were telling us about the different materials on the moon cool at different rates and give us a different picture of what's going on down there. Is that right? Did I have that right?
I actually think I'll let Aaron field that question.
Sorry. Yeah.
No, you're good.
See, Aaron, you didn't think you were going to be on tonight, did you?
As with materials on the Earth, where you have the sidewalk that stays warm throughout the evening versus the beach sand, which gets cool very quickly after the sun goes down, the same type of thing happens on the moon, where you have very fine particles that have what's called low thermal inertia, and they're able to release all of the heat that they're holding rather quickly after the sun stops energizing them. And whereas larger rocks will end up cooling a lot slower. And so things like impact melt and large boulders cool a lot slower than the fine regolith that makes up the surface of the moon.
And is there a particular view of this phenomenon that happens during the eclipse that you would otherwise not see? Is that right?
Yeah, so that's one of the key observations that the Diviner instrument is able to make. It measures the surface temperature of the moon, and when you immediately turn off your light source during essentially at noontime, you're able to get information about what is happening very near the surface in terms of what types and what sizes of rock the materials are there. And so that is what has been going on with the eclipse observations.
Absolutely amazing. Absolutely amazing. You guys always surprise me with what you're able to do. You're capable of doing with this spacecraft. So very, very good job. I'm going to ask the team to come back and kind of help us with questions and polling, and we'll do another session of that.
Actually, Rick, I think we have a presentation before we go into the final break, if I'm correct. I believe the eclipses?
Well, that already happened.
Oh, okay. Okay, well then, yeah, let me get some questions for everyone to answer. That's my bad. Let's see, we still have a lot of questions on the magnetic field. We don't have many about eclipses, unfortunately, so that topic. A lot of people are asking how long does it really take for this magnetic field to flip? I'm assuming that's not between each flip, but actually from when it starts at one pole to the other. That's from Kristen.
I don't know if Katrina is still on or could answer that. So we might have to get back to Kristen on that one. There's also a phenomenon where the Earth's magnetic field sort of flips and things like that. And it's part of the science that I don't understand that. Maybe we can help with that later.
Yeah, and I know, kind of going off some of the earlier questions, a lot of people were asking why it does that, and I think that's kind of one of the great mysteries, as mentioned earlier, because it's impossible to observe the interior of the sun, and it's very hard and difficult to model the interior of the sun. So really trying to figure out what causes the magnetic field to flip relies on that understanding the interior of the sun, and the same thing with Earth. So I think that's part of the difficulty of modeling it and understanding it right now, and that's why it's still a big question that's being studied.
Sounds reasonable. All right. Yeah. And so are there any questions that have come up for LROC?
Nope.
Nope, not yet? Okay.
Nope.
Not quite, but Alex, possibly you could answer a question by Stephen about Hubble, the Hubble telescope, while we wait for some questions about LROC to come in. So if you have questions about the moon, please go ahead and ask those in the Q&A. And maybe Alex can shed some insight onto the emergency shutdown situation of the Hubble Space Telescope.
Yeah, I was actually just looking at that, because this is actually something I hadn't even heard of. I just heard of it when this question, but apparently at some point today, Hubble had a shutdown with one of its computer controls, and There's a theory it's a bad memory board. They tried to restart it, but now they're switching to a backup unit apparently. And then they're going to test it, and then it can resume. If that doesn't work, I'm not sure if they would even consider repairing at that point. Hubble's way past its mission goal, but it looks like they're going to another system and that it'll be fixed up soon. So hopefully that'll all work out. But yeah, I hadn't actually heard of that. So this would just really came out today. So current events.
I am going to kind of just take over here for a little second. Let's see if I can figure out how to share my screen. You'd think I would know how to do that. I wanted to just talk just for a moment about the solstice and what it kind of means and how people celebrate and some of those things. Not a full presentation, but more like just some thoughts about this. This image right here is, of course, a celebration at Stonehenge. This is in the Asbury Plain in England, and everybody knows that. I think everybody knows the nature of Stonehenge. It was actually sort of started back in about 1740. The first idea that this particular monument was actually built as some sort of to capture an event, to capture a solar event. The discoverer at that time, Stukely, actually sort of also thought about it as a monument built by Druids. And it turns out he was wrong about that, but he also, it turns out he was kind of right about that connection with the sun. And then much later, about the turn of the 20th century, Norman Lockyer actually sort of did the calculations, did figure out exactly how the alignment happens and how a summer solstice event happens. Now, the last 2 years, they have been under, or last year, they were under COVID, so people couldn't do the celebration that you see here. This is actually a winter western sunset that you're seeing here. There's also a summer sunrise that happens at this particular monument, and people celebrate both. This year, England is saying, please don't come. We're still not done with COVID yet. They're worried about that. But the fact that human beings sort of find their way to a place like this and celebrate the celebration of the sun that happened in the past, I think is really meaningful to me. And the fact that Stonehenge kind of launched a science about, at the time they called it astroarchaeology. Later people called it archaeoastronomy. And currently the way to use the term is we call it cultural astronomy. Not only studying how past cultures used monuments and used tracking devices and used counting systems to keep track of the sun and solar and nighttime phenomenon, but also how current cultures do that. And so around the world, this particular event is meaningful. To us here in Arizona, it just means it's hot. It's the hottest, it's the longest day of the year. It happens that this year there's a really heat spill that is accompanying the solstice, but that's actually not totally normal. They don't exactly correlate or relate to each other, but that is kind of important. I'm just going to show you a little bit. This is an analemma that tracks the movement of the sun in the sky over the course of a year. The little shape here, as I just mentioned, is called an analemma, and this is basically two different views of it. One is a noontime. The one on the left will be taking an image of the sun approximately every 4 days, in this case, and doing that. Basically, you don't move your camera. You just go out at exactly the same time, and you take a picture of the sun, and then you map all of those images together. And this is really what the movement looks like. The very top of that bowling pin, of course, is going to be the highest part of the sky, or the highest travel of the sun in the sky, and that's going to be the summer solstice. The lowest one down at the bottom is going to be the winter solstice. I'll also say that on the right side of the screen, it's essentially the same phenomenon. It looks like this photographer used a different time scale. This looks like more like 8 or 10 days that he took these images, but it sort of describes to you the same shape. Now, in this case, it's a sunrise phenomenon. So he did this, kind of just after a winter sunrise and started taking these images and did it. But you can see sort of how the sun acts not only in the sky by achieving its highest location, highest above the horizon, and then achieving its lowest above the horizon in the wintertime, and how that movement happens. But you also see how the sun interacts with the horizon here. In the wintertime, the sun sets way, way south, or in this case, rises way south of east. And in the summertime, it rises way, way north of east. And people were able to track that movement as well through the sky. And this is how we sort of understand ancient cultures could essentially watch the seasons, measure the seasons by tracking the sun. And we know that sun phenomenon was watched very carefully over time. The reason the analemma takes this shape is because the sun actually has an elliptical orbit, not a circular orbit. And so by virtue of the laws of physics and Kepler's laws of planetary motion, that means there are periods of the time where the sun moves a little bit slower, or in this case, the Earth moves a little bit slower in its orbit around the sun. And so it changes the time a little bit. The sun will get about 15 minutes behind noon, and it will get about 12 to 14 minutes ahead of noon at certain times of the year. And this really sort of this traces that out. It so also is the reason that the longest day of the year is going to be the solstice. That's going to be Sunday, the 20th, this coming Sunday. But the earliest sunrise and the latest sunset are actually off cycle a little bit. And so if you're looking at the paper and kind of keeping track of that stuff, and you notice that the sun is actually rising a little earlier or a little later, just before or just after the solstice, this is really what's tracking that and what's making that particular phenomenon happen. So I'm going to show you now, if I have time. Oh, no, I don't have time. I'm going to go ahead and just kind of stop share here, close this out. And I know Alicia is going to come back and just talk about some things that are happening in the news. And then I will give you a little preview of the show in 2 weeks, and then we'll call it an hour. Thank you very much.
Thank you, Rick. Welcome to this week's current events. We have a lot to cover. And just a reminder, so tomorrow we have a webinar titled Why We Go Social Futures of Humanity as an Interplanetary Species. And so join a conversation led by Dr. Lindy Elkins-Tanton of the ASU Interplanetary Initiative. And this topic, or this conversation, touches on the topic of the social side of deep space exploration. So that's tomorrow, June 17th, 11 a.m. to noon. So make sure you register for that. We should provide the link in the chat. So keep an eye out for that.
So take a look.
Perfect. Kim is on it. Next, the Arizona Historical Society opened a space exhibit almost a month ago. And what's really neat is that ASU is featured in it. And so it is down in Tucson. And if you're able to go, it's running through the end of November. And so we highly encourage you to take a visit if you can. And it is titled Ready to Launch Arizona's Place in Space. So go ahead and check that out. And then next, hot off the press, we have a new course offered at ASU School of Earth and Space Exploration titled Introduction to Space Weather, Explores Space Weather and Solar Systems. And so this course is going to be taught by our very own assistant professor, Dr. Katrina Bossert. So we're very excited to have this course offered this fall and to learn more about space weather. So, and Rick briefly touched on it at the beginning of our show, but we are sad to say that Sporty is leaving us. This is her last show. She has been with us for so long, and she has been absolutely instrumental in every way imaginable. We couldn't have done Virtual Night Skies without her, and she's been here from the beginning. So we want to thank you so much for all of the work that you've done, and we will definitely miss you. But we will keep tabs on you for sure. So thank you.
This is so sweet. I was not expecting this. Thank you.
You well deserved, Spurty. You've just been
Thank
a
you.
really, really great student, and
Thank you.
she's helping me right now with a really huge project. When everybody gets back to campus, we've recreated all the content on our magic planet, the ball that's in the middle of the atrium, and Spurty headed up that project, and she's done an amazing job. And then, and you're graduating, so tell everybody what you're graduating with and where you're headed.
So I will be graduating with a master's degree in aerospace engineering, and I will be working for a company called Sandvik, and I'll be working in the capacity of a thermal engineer for their material science R&D. So it's going to take me all over the globe, and I'm excited. And thank you so much for this. I'm going to stop video before I start crying.
Oh, Spurty, it's been great. And you have been with us since the very, very first show. So we've been doing this a little bit more than a year. Thank you for all your help. I really appreciate it. So
thank you so much.
So
Thank
this
you.
is what we do at ASU. And students become really good and really helpful when they graduate. They go someplace else. But that's life. So in 2 weeks from today, I'm going to take a little time off. I'm not sure whether I can actually log in or not. I'm going to be in the area of the north rim of the Grand Canyon, and I'm going to be doing some astrophotography, and you're going to see a little bit of that later in the summer. But not to worry, we are doing our program. So 2 weeks from tonight, on the 30th of June, our third program in the month of June, we're going to feature actually the Center for Meteorite Studies. And the curator of that program is a gentleman named Lawrence Garvey. And Lawrence has agreed to give you guys, everybody, an extra special tour of the meteorite vault. And so we have a display for the public to come visit when we're open, and we will be open again eventually. But very, very few people actually get back into the vault, into the place where they keep the specimens and they keep some of the science protected. And Lawrence will give us some insight into that. So really, really looking forward to that. If I can join, I will. I want to see it, but you'll be in good hands. And Kim will be sending out the reminders and the links as we go. And then I will remind you, you're going to get a message from Kim in a couple of days. And she's going to ask you if you have any comments or questions, or if there's anything you'd like to see in the future, or any comments about the program as we have it. Please take advantage of that. We do take those seriously. We look at all that information, and we do use it to sort of like set our minds towards programming in the future based on what the audience tells us they want to see now. So thanks for that. Unless there is something else and my team wants to chime in, I'm going to go ahead and sign out 2 minutes after the hour. Thank you very much. And don't forget, on the 20th, we're going to celebrate the longest day of the year, the summer solstice. And then the good news is that the sun starts moving back towards the south immediately afterwards. And so we will see a fall in about 3 months. We will see a winter in about 6 months. And that's the way the cycle works. Thank you very much for joining us. And we'll see you next time. Thank you.